Generally 12 volts direct current is considered safer than 24 volts direct current due to its lower potential to cause electrical shock, especially in wet environments. The higher the voltage, the more current can flow through the human body, which increases the risk of injury. Solenoids require a certain amount of current to operate properly. Lower voltages require higher currents to achieve the same power. Therefore, 24 volts direct current solenoids will draw less current than 12 volts direct current solenoids, which can be beneficial for reducing electrical losses and overheating. The National Electrical Code, NEC, does not have a specific voltage limit for control lines. However, it does recommend using low voltage systems for control circuits in wet or hazardous locations. Some local health codes may have specific voltage requirements for water park installations. It is essential to check with the local health inspector to determine if any such requirements exist. If you need to make a case for 24 volts direct current, firstly, emphasize the lower shock hazard associated with 12 volts direct current, especially in the wet environment of a water park. Secondly, explain that 24 volts direct current solenoids draw less current than 12 volts direct current solenoids, reducing electrical losses and overheating. Thirdly, if possible, find industry standards or other references that support the use of 24 volts direct current for control lines and water park installations. Fourthly, provide examples of successful 24 volts direct current control systems in similar water park environments. Finally, conduct a risk assessment to evaluate the potential hazards associated with both 12 volts direct current and 24 volts direct current systems and demonstrate that 24 volts direct current poses a lower risk. The inspector makes the final decision of allowing the use of 24 volts direct current control lines. To understand the nuances, let's delve deeper into the factors at play. We'll start with voltage and current. Voltage can be thought of as the electrical potential difference, the driving force that pushes electrons through a conductor. Measured in volts, a higher voltage implies a greater potential for electrical energy to be transferred. Current, measured in amps, is the rate of flow of electric charge. It's the number of electrons passing a given point in a circuit per unit of time. The relationship between voltage, current, and resistance is defined by Ohm's law, which states that voltage equals current times resistance, or volts equals amps times ohms. This fundamental law dictates how these three quantities interact in an electrical circuit. Power, measured in watts, is the rate at which electrical energy is transferred. It's calculated as voltage times current, or watts equals volts times amps. In the context of solenoids, power determines how much work the solenoid can do, such as opening or closing a valve. Now, let's consider the human body's response to electricity. Electrical shock occurs when current passes through the body, disrupting normal bodily functions. The severity of the shock depends on several factors, including the voltage, current, path of the current through the body, duration of exposure, and the individual's physical condition. Higher voltages have the potential to drive more current through the body, increasing the risk of a severe or even fatal shock. However, it's important to note that current is the primary factor determining the severity of the shock. Even relatively low voltages can be dangerous if they can deliver a sufficient amount of current. Dry skin has a relatively high resistance, which limits the amount of current that can flow through the body. However, wet skin significantly reduces resistance, making it much easier for current to flow. This is why the risk of electrical shock is much higher in wet environments such as water parks. Therefore, in such environments, safety precautions are paramount. When selecting a voltage for control circuits, it's essential to consider the potential for electrical shock, especially in wet conditions. While 12 volts direct current is generally considered safer than 24 volts direct current, it's not entirely risk-free. Both voltages can potentially cause a shock if the conditions are right. The key is to minimize the risk of exposure and ensure that appropriate safety measures are in place. Now let's address the specific requirements of solenoids. Solenoids are electromagnetic devices that convert electrical energy into mechanical motion. They consist of a coil of wire wrapped around a movable plunger. When current flows through the coil, It creates a magnetic field that pulls the plunger into the coil, causing it to move. Solenoids are commonly used in water parks to control the flow of water in water cannons and other attractions. They require a certain amount of current to operate properly. The amount of current required depends on the solenoid's design, including the number of turns in the coil, the size of the wire, and the strength of the magnetic field. Lower voltages require higher currents to achieve the same power output. This is because power equals voltage times current. If the voltage is reduced, the current must increase to maintain the same power level. For example, a 12-volt direct current solenoid will draw twice as much current as a 24-volt direct current solenoid with the same power rating. This can have several implications for the design of the control system. Firstly, higher currents can lead to increased electrical losses in the wiring. Electrical losses occur when current flows through a conductor, such as a wire. The resistance of the wire converts some of the electrical energy into heat, which is dissipated into the environment. The amount of electrical loss is proportional to the square of the current. This means that doubling the current quadruples the electrical losses. Higher electrical losses can reduce the efficiency of the system and increase energy consumption. Secondly, higher currents can cause the wiring to overheat. When current flows through a wire, it generates heat. If the current is too high, the wire can overheat, potentially damaging the insulation and creating a fire hazard. The amount of heat generated depends on the current, the resistance of the wire, and the duration of the current flow. To prevent overheating, it's essential to select wires with an appropriate ampacity rating. Ampacity is the maximum amount of current that a wire can safely carry without exceeding its temperature rating. The NEC provides tables that specify the ampacity of different types of wires based on their size, insulation type, and installation method. Thirdly, higher currents can require larger wires and more robust components. Larger wires are needed to handle the increased current flow without overheating. More robust components such as switches, relays, and power supplies may also be needed to handle the higher current levels. This can increase the cost and complexity of the control system. When choosing between 12 volts direct current and 24 volts direct current for solenoid control, it's important to weigh the safety considerations against the potential efficiency and cost benefits. While 12 volts direct current is generally considered safer from a shock hazard perspective, 24 volts direct current may offer advantages in terms of reduced current draw, lower electrical losses, and smaller wire sizes. It is a matter of understanding the trade-offs. Now, let's examine the relevant electrical codes and standards. The NEC is a widely adopted standard for electrical installations in the United States. It provides comprehensive requirements for the safe installation of electrical wiring and equipment. The NEC does not specify a specific voltage limit for control lines. However, it does recommend using low-voltage systems for control circuits in wet or hazardous locations. Article 725 of the NEC covers Class 1, Class 2, and Class 3 remote control, signaling, and power-limited circuits. Class 2 and Class 3 circuits are considered inherently safer due to their limited power and voltage levels. However, they may not be suitable for all solenoid control applications, particularly those requiring higher power levels. The NEC also addresses wiring methods for wet locations in Article 300.6 and other relevant sections. It specifies requirements for using water-resistant or waterproof wiring and enclosures to protect against moisture damage. Local health codes may also have specific requirements for electrical installations in water parks. These codes may address issues such as shock protection, grounding, and bonding. It's essential to check with a local health inspector to determine if any such requirements exist. Now, let's discuss strategies for convincing the inspector that 24 volts direct current is a safe and efficient option for your water park installation. Firstly, emphasize the reduced current draw of 24 volts direct current solenoids. Explain that this can lead to lower electrical losses, reduced wiring costs, and improved energy efficiency. Provide calculations to demonstrate the potential savings. Secondly, highlight the benefits of 24 volts direct current in terms of reduced voltage drop. Voltage drop occurs when the voltage at the end of a long wire run is lower than the voltage at the source. This can affect the performance of solenoids and other electrical equipment. Using a higher voltage, such as 24 volts direct current, can help to minimize voltage drop and ensure that the solenoids receive adequate power. Thirdly, present data on the safety record of 24 volts direct current control systems in similar water park environments. If you can demonstrate that 24 volts direct current has been used safely and effectively in other installations, it may help to alleviate the inspector's concerns. Fourthly, conduct thorough risk assessment to evaluate the potential hazards associated with both 12 volts direct current and 24 volts direct current systems. The risk assessment should consider factors such as the likelihood of electrical shock, the severity of potential injuries, and the effectiveness of safety measures. The risk assessment should demonstrate that 24 volts direct current poses an acceptable level of risk. Fifthly, offer to implement additional safety measures to further reduce the risk of electrical shock. These measures could include using ground fault circuit interrupters, GFCIs, installing barriers to prevent access to live electrical parts, and providing training to employees on electrical safety procedures. Finally, be prepared to compromise. If the inspector is unwilling to approve the use of 24 volts direct current, you may need to consider alternative solutions such as using 12 volts direct current with enhanced safety features or using a different type of control system altogether. Ultimately, it's the local health inspector's decision whether to allow 24 volts direct current control lines. However, by providing these arguments and demonstrating a commitment to safety, you can increase the likelihood of convincing the inspector that 24 volts direct current is a safe and efficient option for your water park installation. To summarize, the decision between 12 volts direct current and 24 volts direct current involves balancing safety considerations with efficiency and cost factors. While 12 volts direct current is generally considered safer, 24 volts direct current can offer advantages in terms of reduced current draw, lower electrical losses, and smaller wire sizes. By understanding the relevant electrical codes and standards, conducting a thorough risk assessment, and implementing appropriate safety measures, you can make an informed decision that meets the needs of your water park installation while ensuring the safety of employees and patrons. Remember to consult with qualified electrical professionals and local authorities to ensure compliance with all applicable regulations. This information is intended for educational purposes only and should not be considered a substitute for professional advice. Always consult with qualified professionals before making any decisions about electrical installations.